Okay, we're ready to start 8.4, other convergence tests. So at this point, pretty much every test that we've been running has assumed that the series that we have contains positive terms. So in other words, the sequence, the A sub n, is only positive numbers. So in this section, we're going to be looking at how we can handle a series where the terms of the series could possibly become negative. So the first definition here is the definition of an alternating series. Now, we've already seen what an alternating sequence is back in 8.1, but here we're talking about an alternating series. So whenever we have a series that can be written in a way that we have -1 raised to the n power, that will create a series where your first term is negative, then the next one's positive, then negative, then positive, then negative. And then the B sub n here is actually a formula for the number you get. And that number can, can be anything, be 1 over n squared or whatever it is. But that part of it now we have to look at as always being positive, right? So the only part of the series that is impacted, or what makes the series alternate, is this -1 to the n, but this B sub n is going to be some positive number. Now, we could also have the series start off with a positive, and in that case, we would need it to look like -1 to the n minus 1. We could also use n plus 1, but that will start us out with positive numbers, and then a positive number, then negative, then positive, negative. Again, assuming this B sub n is some formula, 1 over n squared, 1 over n cubed, whatever it is, but that part's always positive. So it's only this -1 to the n minus 1 that's causing the alternating. Okay, so every series that we call alternating is going to be in one of these two formats. Now, here's some examples of alternating series. -1/2 plus a third minus a fourth plus a fifth minus 6 plus a seventh. Here's the formula for that. So this -1 to the n will create the alternating starting with negative, and then 1 over n. You know what? I'm missing. This is off. Okay, oops. I'm going to have to change this. Make this n plus 1. That's how I'll fix it. N plus 1. There. Now, when you plug in 1, you get 2, and then plug in 2, you get 3. And then this one's wrong too. I'm going to change that to a +1 also. Okay. All right. So these two would these are the series that are created, and then this part right here. This is the B sub n, and this is the B sub n, and that's the part that creates the alternating, right? So here, B sub n in both of these examples is the 1 over n plus 1. So I guess what we're trying to be able to do here is, with an alternating series, be able to separate the -1 to the n part from the rest of the formula. And that way we can focus our attention on this piece right here, which is our B sub n. All right, so now, what do we do? How do we figure out if an alternating series is converging or diverging? Well, we have all those tests from the last sections can't be used because they assume that the pieces are positive. So here we have our first test that deals with this, and it's called the alternating series test. Abbreviate that AST. So the alternating series test says, hey, if you're given a series that alternates like this, or if you have, the other way where it starts off positive here, this one starts negative, this one starts positive. In either case, if these two conditions below are true, then the series converges. So we have a very quick, easy way to check whether or not an alternating series converges or diverges. What we do is we say, all right, first condition, we need B sub n to be greater than or equal to B sub n plus 1. So we looked at that back in 8.1. All this means is that the sequence is decreasing. So we just have to be able to show the sequence decreases. And then the last part is we have to show that the limit of the sequence is 0. So if we take that formula, whatever it is, that piece sitting on the outside, we take the limit as n goes to infinity. If we get 0, then we've got convergence of the series. So super nice test. So here's an example here. Let me take both of these. Do these series converge or diverge? Okay, here we go. So the first series we're looking at here is known as an alternating harmonic series. Recall that the harmonic series looks like this. Sum n equals 1 to infinity of 1 over n, and that gives you 1 plus a half plus a third plus a fourth, and that's harmonic That's what we call our harmonic. And we know that that diverges. This, though, is basically this series. And now I'm starting, this one starts at 1/2, but we already talked how if you just are missing one piece, doesn't impact the convergence or divergence. So we're missing the one, but other than that, it's this series, but with alternating signs. So this would be known as an alternating harmonic series. So let's figure out if it converges or diverges. First, let's write the series out in a formula. So I want it to start positive, so -1 to the n, let's go +1. And then times, here's the b sub n, the part that generates all the numbers, 1/n + 1. So that should start us out with 1/2, then 1/3, then 1/4, and it will create the alternating. So now we run the alternating series test. Please keep in mind, this is our b sub n. So if I run the alternating series test, what I'm going to do is the first condition is I want to show that b sub n is greater than or equal to b sub n + 1. Okay, so I want to show that it decreases. So b sub n is just the formula. And then b sub n + 1, hold on a second. Yeah, okay. The b sub n + 1 is this formula with n + 1 plugged in. So we get 1/n + 1 + 1. So we need to show that 1/n + 1 is bigger than or equal to 1/n + 2. And if we do our little cross multiply, we get n + 2 is greater than n + 1. And I think we can subtract n on both sides, subtract 1 on both sides. We get 1 is bigger than or equal to 0. That's true. So it does decrease. Okay, first condition is met. Now we just need to take the limit as n goes to infinity of b sub n, and that goes to 0. So check, both of the conditions of the alternating series test are true, or the conditions are met, which means, therefore, the original series converges. There we go. All right, now let's do the next one. So for the next one, we have this series. It alternates because we got -1 to the n + 1, and that's n² + n³ + 1. So here's our b sub n. So first thing, I'm going to do alternating series test. I'm going to try the first condition. You know, we want to show that b sub n is greater than or equal to b sub n + 1. So we want to show that n² / n³ + 1 is bigger than or equal to, now we have to replace the n's with n + 1s. So n + 1² over n + 1³ + 1. Okay, and now, boy, this is going to be a mess. Let's expand out on the right-hand side. Let's do this multiplication. And let's see, n² + 2n + 1 on top. And then we have to cube this. That'll give you n³ + 3n² + 3n + 1. I'm doing that mentally. You can do it by hand on the side, then +1 here. That's this +1 there. And now we can do this cross multiply. So if I multiply, let's put those two together. 1 + 1 is 2. Okay. If I multiply this times that, basically hit this with n², I get n to the 5th plus 3n to the 4th plus 3n to the 3rd plus 2n² must be greater than or equal to. Then I have to multiply this times this. So I have to multiply that times n³ + 1 to get it out of here. So when we do that, we're going to have to expand this. So we get n to the 5th. Okay, so I did here to here, and I'll do here to here, so plus n². And then here to here, so plus 2n to the 4th, and then plus 2n, and then plus n³, and plus 1. Okay, let me collect some like terms together here. N to the 5th, plus 3n to the 4th, plus 3n³ plus 2n² must be greater than or equal to n to the 5th plus 2n to the 4th plus n cubed. Oh, I thought I had some like terms. I guess we don't. Plus n squared plus 2n plus 1. All right, let's see, I think we might get some things to cancel here. We got n to the 5th on both sides, so that goes away. Let's see, let's subtract 2n to the 4th on both sides. We get n to the 4th. Let's subtract n cubed on both sides. We get plus 2n cubed. Let's subtract n squared on both sides. I get plus n squared. And let me see, I can, this 2n here, I guess what I can do is I can leave that on this side, 2n plus 1, because if I subtract, it's going to become negative. Let's notice that the left side is n squared times n squared plus 2n plus 1. Okay, that is bigger than or equal to 2n plus 1. All right, is this true? Let's just think about this. This is linear on the right side, so it's not going to grow very fast as n gets big. This is the 4th power. It's going to grow very quickly. Let's check it for n is 1. Let's see what we get here. We get 1, and then here we get 1 plus 2 plus 1. So we get 4, and then that is greater than or equal to, if we plug 1 in here, we get 2 plus 1, that's 3. That checks. And then once we get to 2, the left side is going to get huge. So 4, 2 times 2, 4 plus 4 is 8, 9. So 4 times 9 greater than or equal to 2, 4, 5 over here. That's true. So then it's going to just take off. So this is true. We're happy about this. I'm trying to think of another way we could have done that. Yeah, no, that's good. Okay, so first thing we want to show is that it's decreasing. We showed it's decreasing. The next thing we want to show is that we want to show that it is, that the limit as n goes to infinity of the sequence itself, which was b sub n, n squared over n cubed plus 1. We want to show that that's 0. So you get infinity over infinity. So you'll have to do L'Hopital. And you'll get 2n over 3n squared. And then an n cancels there. And you just get 2 over 3 to the n. Let n go to infinity. This goes to 0. And that checks out. So both conditions are met. So by the alternating series test, therefore, the original series, what was it? Tn plus 1 over n squared over 3n, or sorry, n cubed plus 1 converges. All right. Nice test. Nice test. All right, let's see what else we got here. Okay, now, we've already said that when we're doing these tests, all we can determine is convergence or divergence, but we can't actually figure out what the sum is, right? Well, there is this thing called alternating series estimation theorem, all right? And so this theorem is really kind of weird. It's difficult, not difficult to use, it's awkward, okay, when students see it for the first time. So, you know, the theorem just says that if we have a series and it satisfies the conditions of the alternating series test. So we're talking about like the 2 examples we just did, right? For these 2 examples, these both satisfy the conditions for the alternating series test. That means they both converged. This says if that's true, if we do have that they satisfy the theorem, then we can estimate the sum. We can actually estimate what the sum of the whole thing is. Now, it's still not the exact sum, but it's an estimation, and we can estimate it as closely as we ever need to estimate it. So let me give you the theorem. Okay, so it says first, given an alternating series, by the way, this only works for an alternating series. Given an alternating series, if the 2 conditions of the alternating series test are true, okay, so those are the 2 conditions we just went through. If that's true, then, all right, so this is weird. Just ignore this for right now. It says that S, that's the true sum of the series, minus S sub n. Now, S sub n, recall, is the nth partial sum. This is not the whole series being summed. It's stopping at n. Okay, it's whatever your sequence or series is here. Oops, K, I think base of K. It's you add up the first one and the second one, but you stop at K, the kth one. This says that if you look at the difference between the true sum and the partial sum, okay, that will always be less than or equal to b sub n plus 1. okay, what in the world are they talking about here? So I think it's best if we just kind of show, if I show you an example. So I've got a specific example here. Where is it? Okay, it's a really kind of weird one. I'm going to need to clear the screen. So let's say we want to look at sum n equals 1 to infinity of -1 to the n times n over n factorial. And we want to find the sum. We want to actually find that sum correct to 3 decimal places. Okay, so here's what the theorem is saying. If this right here, so if this satisfies the alternating series test conditions, if it does, then whatever this sum is, okay, the difference between that and finding the sum, but only out to the nth term, okay, whatever this is, that difference will always be less than or equal to b sub n plus 1. Now, b sub n plus 1 means if we start writing these out, right, because remember, this is this right here, this right here is our b sub n, okay? So what we're doing is we're looking at just the positive parts here. If we go out and we take the n plus 1 of that, it's going to be some number. That number will always be bigger than the difference between the true sum and the approximate sum, the nth partial sum. Okay, I know this is still confusing. All right, so I think we're just going to have to do that example. So first things first, let's take a look at this right here. Let's make sure you understand that b sub n is n over n factorial. That's the positive part. Okay, first I have to show the alternating series test. The conditions are met. So first show it's decreasing. So we plug n in, and then we plug n plus 1 in. Oops, did I forget to put n plus 1? I did forget to put n plus 1 there. Ooh, okay, you know what? I'm gonna have to do that on another page then. Okay, we have sum n equals 1 to infinity, -1, what was it, to the n or n plus 1? To the n, and then n over n factorial. All right, so first, it is an alternating series. So let me do the first condition. Let's show that b sub n is bigger than or equal to b sub n plus 1. So if b sub n is this part, so just plug n in, show that that's bigger than n plus 1 over n plus 1 factorial. Let's do this. Yeah, well, I guess we can cross multiply n times n plus 1 factorial bigger than or equal to n times n plus 1. No, n factorial times n plus 1. Okay, so you cannot easily figure this out. I think maybe the best thing to do here would be to divide both sides by n factorial, and then use a property we learned a while back about this. N plus 1 factorial over n factorial equals n plus 1 times n factorial over n factorial. They cancel, so that's just n plus 1. So you have n times n plus 1, these cancel, is bigger than or equal to n plus 1. Divide both sides by n plus 1, and you get n is greater than or equal to 1. That's true. So we know that the first, it's decreasing. That's the first condition of the alternating series test. The second condition is that the limit as n goes to infinity of this thing, b sub n, goes to 0. And you can't use L'Hopital because you can't take the derivative of a factorial, but you can do this. You can rewrite the bottom as n times n minus 1 times n minus 2, down to 1. The n's cancel, you get a 1 up here, and now when n gets big, you got this going to infinity, and the top is fixed at 1, so that goes to 0. So that is, again, satisfied. So we know this series satisfies the alternating series test, therefore we know it converges. We are going to approximate it, okay, by saying that the true sum minus the nth partial sum must be less than or equal to b sub n plus 1. And what we need, or what we've been asked, is to try and find this sum correct to 3 decimal places. So when you think about a number, right, the decimal places, whatever this is, we want our approximation to be good enough that those 3 decimal places do not, like those are correct. The others might be wrong, but the first 3 decimal places are correct. So we want the difference between these two to be smaller than, we want this to be smaller than 0.0001. Because if the difference between this is less than 0.0001, then we know that the difference of those are, they're correct. Okay, they're correct. They correspond at least in the first 3 digits of the decimal. Other than that, they might be off a little bit, but that's pretty accurate. So what we do now is we say, all right, well, that means I need to figure out when this, if I can make that less than that, then I know that the difference between these is less than that. So what is b sub n plus 1? Well, b sub n plus 1 is our original formula for b sub n with n plus 1 plugged in. So we plug in n plus 1 on top, we plug in n plus 1 on the bottom, right? And we want that to be less than 0.0001. So now the question is, how do you do this, right? How do you figure out what n is here? Well, you're just going to have to play with it a little bit. So if I kind of mess around here, let me see left side, let me rewrite the bottom as n plus 1 times n factorial. I can do that because of properties of factorials. Then the n plus 1's canceled. So I get 1 over n factorial must be less than 0.0001. I can multiply both sides by n factorial. And then to get rid of this decimal, I'm going to multiply both sides by, let's see, 10, 100, 1,000 by 10,000. So if I multiply by 10,000 here, then I get n factorial must be bigger than 10,000 for this to be true. So now you can start to kind of mess around with factorials. You know, you get your calculator out. Let me try, let's see, if you do, let's try 5 factorial. Is that big enough? Let's see, 5 times 4 times 3 times 2 times 1, that's 120, not good. How about 8 factorial? 8 times 7 times 6 times 5 times 4 times 3 times 2. So 8 factorial, this is 120 by the way. 8 factorial is 40,320. That's way bigger than I need it to be. How about 7 factorial? Okay, so 7 factorial is only 5040. So that doesn't seem big enough. So we would need our n factorial to be 8 factorial, right? Which means that n would have to be 8 for this to work. Which means that if we put 8 in here for this, that means if we take the 9th term, right? Sorry, hold on. We wanted the b, so yeah, so we want n to be 8. So that means that we want s of 8. If we did the partial sum out to the 8th term, that should be less than 0.001. So what I'm going to do now is I'm just going to kind of write down what that is. If we take the sum n equals 1 to 8 of the original series, which was -1 to the n times n over n factorial, yeah. Okay, we want to stop at 8, right? Then that should be close enough. That should be within 3 decimal places of the true sum. So this means I plug in 1. If we plug in 1, we get a negative number. We should get -1. If we plug in 2, we get positive, and then we get 2 on top and 2 on the bottom. So you get another 1. Then a minus, now we plug in 3, so we should get 3 over 3 factorial. This was 2 over 2 factorial, but those are the same. 2 and 2 factorial are the same, that's why that's a 1. So we get -1 plus 1, and we want to do the first 8 of these. If we do the first 8 of these, we're in business. So I already did this for us so that you can see it. If we go out, if we do the first 2, it was -1, then 1. If we do the next one, that's 3 factorial, or 3 over 3 factorial. And keep going, let me go to the 8th one. If we do the sum of the first 8, here's the sum of the first 8 right here. then our answer, if we were to add all these up, I have the computer doing it already for us, you see that the nth partial sum is negative 0.367855714. It's negative because some of these terms are positive, some are negative, but here's the whole point of this. This right here, 0.367, these, no matter if I keep adding more, these first three terms aren't going to change. Okay, the others might, but the first three are locked in, no matter how far it goes. So if I wanted to be accurate within the first three decimals, then I only needed to go out and do the first 8 terms. Let me back it up. So right here, here's the first 6 terms, right? I'm at 0.366 or negative 0.36666. If I go 1 to 7th term, I get a negative 0.368. And then the 8th term, there I'm guaranteed right there that anything further than that, first 3 terms aren't changing, okay? Here, 0.368, not good enough. It's gonna change the next time. I get the 8th one, 0.367 is not going to change no matter how far I go out. I hope that makes sense. You have a few of these on your homework to try, see how it goes. I'm going to take a quick break. Okay, we're moving on. We got some definitions now that we need to establish before we can continue. So the first definition, sounds like my neighbor's about to start mowing the grass. Hold on, let me shut the window. Okay, while I was taking a break, I decided, you know, I'm gonna do another one of these just so you can see it work from the beginning. So here's a way the problem would appear, like in the textbook. It says, here's a series, and it wants you to find basically how far you need to sum this out to in order to make sure that the sum you take is within 0.0001 of this true sum. So whatever this is, all right, that's our true sum. And the difference between that and the nth partial sum is always less than b sub n plus 1, so long as this satisfies the alternating series test criteria. So we need to look at this. We need to figure out what the b sub n part is. The b sub n is the positive part, so we'll ignore this. We've got 1 over n times 5 to the n. Now you need to show, first of all, that it's decreasing. So we need to show that b sub n is bigger than or equal to b sub n plus 1. And I was thinking you can also just show it strictly increasing, or strictly greater than, which means that it's decreasing, they're never equal to one another. It won't matter because n and n plus 1, you get 2 different answers. So they won't ever be equal. All right, so if I plug in n here, I get this. If I plug in n plus 1, I get 1 over n plus 1, 5 to the n plus 1. And so let me just rewrite this. This is 1 over n, 5 to the n. I need to show that that's bigger than 1 over n plus 1 in parentheses. Oops, I need that in parentheses. And then 5 to the n times 5 to the 1. That's splitting that 5 to the n plus 1 up. Now I can multiply 5 to the n on both sides, and it'll cancel those out. So I have 1 over n is bigger than 1 over 5n plus 5. So all I did was distributed this 5 through to both of those. And now I can cross multiply 5n plus 5. It's bigger than n. And then I can subtract n. So 4n plus 5 is bigger than 0, and that is true. So it is decreasing. Second thing, take the limit as n goes to infinity of the sequence b sub n. And that is obviously going to a fixed number over infinity. So that goes to 0, so that checks. So it satisfies the criteria of the alternating series test. So the true sum, the difference between the true sum and any nth partial sum we take will always be less than b sub n plus 1. So we need to figure out what's going to make this b sub n plus 1. We need that to be less than 0.0001. If we can do that, we're guaranteed that we've found the sum far enough. Well, then we'll be able to figure out what n is, and then that'll tell us what this n is. So b sub n plus 1, we did that over here. We need 1 over n plus 1 plus 5 to the n to be less than 0.0001. So I can start to algebraically start messing with this. Or I can just start getting on my calculator and trying some values of n into this. So let me try n equals, let's go with n equals 3 first, because I'm just kind of guessing here, but that seems like that might work. 3 plus 1 there and 5 to the third. Let's see what we get there. So this is 1 over 4 times 5 cubed is 125. So this is 1 over 500, right? I don't think we're quite there yet, right? So let me see here. I'm trying to think of if I should go for, well, how much further I need to go. Yeah, this is only 0.002. So we need to go further. Let's try, this was n was 3. Let's try n is, let's go to 5. Okay, so this will be 1 over, let's see, 5 plus 1, and then 5 to the, I forgot to put n plus 1 up there. Shoot. Okay, n plus 1 there. Oops, this should have been a 4. Oops, that actually might get us there. Hold on. So this is still 4. This is 4, 5 to the 4th. My apologies. So when we do 5 to the 4th, right, that's 625 times 4. This is 1 over 2,500. All right, 1 divided by 2,500. That's equal to 0.0004. Okay, that's not less than 0.0001. So I think we're gonna need one more. So let's go to the n equals 4. If we do n equals 4, we get 4 plus 1, 5 to the 4 plus 1. So 1 over 5 times 5 to the 5th. And then that'll be 5 to the 5th times 5. So this is 1 over 15,625. I think we're there. Yeah, this is 0.00064. Definitely got your first 3 to be, or actually this number right here is smaller than 1 because you're trying to get to 0.0001. So we're good here. Looks like n equals 4 will be good enough, which means that all we have to do is sum this up to the first 4 of these. So I'm going to start sum n equals 1 to 4 of -1 to the n over n5 to the n. Okay, let's plug in 1. If we plug in 1, we get a negative on top. Plug in 1 down here, we get 1, we get 5, -1/5 plus. Okay, because when we plug in 2, we're going to get a positive number. So we get a plus on top there. And now we're plugging in 2 here, so 2 times 5 squared. Now minus, and then we get 3 times 5 to the 3rd. And then we get plus. We're going to stop at this one, 4. So we get 1 over 4 times 5 to the 4th. All right, I'm going to get this. I'm going to get on my calculator and do this. -1/5 plus 1 over, that's 25 times 2, that's 50, minus 1 over, let's see, that's 125 times 3, so 375. And then plus this one right here is going to be 1 over 4 times 5 raised to the 4th. Oops. And it messed up. Sorry. What the heck? I don't use this calculator now. Oh, there we go. 5 raised to the 4th. So there we go. Something is messed up. Pause for a second. Okay, I figured out on my calculator, there's a weird button on there. I don't use this one very often. It's messing me up. Okay, so we figured out that we only have to sum the first 4 terms to be within this much of the original or the true answer. So I did the first 4 terms, I converted these to decimals on my calculator, and then I got this. So what we know is that this is within one, let's see, what is this? Tenths, hundredths, thousandths, within 1/10,000. So if I go out to the 10,000th position, that right there should only go up or down by 1. That's it. So the first 3 digits are good. That one can only fluctuate a little bit, 1 up or 1 down. And if I go out further, I'll get more accurate. So that's the whole idea, is just that you understand that there's an easy way to figure out how far you need to go out, rather than you just kind of guessing, oh, you know, like, how close is that to the real answer? All right, I hope that helps a little bit. All right, back to the notes here. So definition. Okay, we move to a new definition. So now we talk about any series, not alternating series anymore, just any series at all. If we're given any series, all right, what we want to do is we want to look at a new series. This is a similar series, and what it is it's the same summation, but instead of looking at the a sub n by itself, we're going to look at the absolute value of the a sub n's. If we look at the absolute value of each one, then what it's doing is it's saying, who cares if it's positive or negative? Let's just make them all positive. Okay, this is a new series. It's just, like I said, the sum of the absolute values of the terms of the original series. All right, that's what that notation means, right? So we're going to look at that now. What we want to do is define something. A series, okay, so if you're given some series, we will say that it is absolutely convergent, okay? That's the term. If the sum of the absolute values of that series converge, all right? If that series converges, then we will say that the original series is absolutely convergent. So let's do an example, all right? So if we take a look at this example, I think I'll do this on another page. If we look at the series, sum n equals 1 to infinity, -1 to the n over n squared, we can see here that this is an alternating series. So we can run the alternating series test on this, but that's not what I want you to think about. Right now, I want you to look at the sum from n equals 1 to infinity of the absolute value of this thing. And when you take the absolute value and on the top, it's always, no matter what's happening with the -1, it's always going to spit out a +1. So this is really going to turn into this series. And that's a p series, with p being 2, which is greater than 1, so it converges. So when we started with this series, we took a look at this new series, which is the series of the absolute value of the sequence here. And we looked at that and we said that it was convergent. What does that mean? It means that we can say that this, okay, the terminology here, that is absolutely convergent. Okay, it doesn't, right now, it doesn't, we're not talking about the convergence of this. We're saying this, if this absolute value of it, if that gives you something convergent, then we will call this thing absolutely convergent. All right, that's it, it's just a definition. Let me show you a different example. -1 to, yeah. Okay, so what if we do the same thing, same problem, okay? We're gonna change one little thing on it. So we're gonna go sum n equals 1 to infinity. Let's go -1 to the n over just n, not n squared. Now, if we look at the sum of the absolute value, when we take the absolute value of this, we no longer have to worry about the -1. So we just get 1 over n, and this is harmonic, and it diverges. So what can we say, right? Well, what we can say is that this series, right, is not absolutely convergent, because the series of the absolute value doesn't converge. So we just say it's not absolutely convergent. That's it. All right. So this is just terminology. That's all this is. Now we have this thing called conditional convergence. So given any series, we will say the series is conditionally convergent if it itself is convergent, but it is not absolutely convergent. Okay, what do we mean? All right, so conditional convergence means that it itself is convergent. Okay, so this one itself is convergent, right? We could go back and we could look this, we could do this with the alternating series test. I'm not going to do it, but we could show that this converges. So to say it's conditionally convergent means that it is, this converges, yes, but not absolutely convergent. So when we do this, we don't get convergence. So this one does, it converges in both cases. So this one is not conditionally convergent. This one, however, is, because this right here, by the alternating series test, I won't show it, is convergent. That's the alternating harmonic. We did that example already. So this is convergent. And when you look at the absolute value of it, right, it's divergent. This is what conditional convergence is. It's when the original series converges, but it doesn't converge absolutely. So this is what we consider, what we call conditionally convergent. All right, not conditionally convergent, conditionally convergent. All right, now a theorem. This theorem says, if you have a series, if it is absolutely convergent, then it itself is convergent. All right, what is this theorem saying? It's saying if you go and you take any series and you go do this absolute value thing, if it converges here, that guarantees it converged there. So notice this one converged here, then this theorem says positively that must converge. Notice that this one here diverged, right? The theorem tells us nothing, okay? If it diverges, the theorem is not saying anything. It's just saying that if it converges absolutely, then the original series must converge. So this is a way of checking for convergence on things. Watch, I'll show you. We'll do this example here. This is a nice one here. So let's figure out if this converges or diverges. Well, first thing we have to notice is that these terms here in here are not always positive, because sometimes sine is positive, sometimes sine is negative. It's also not alternating. It doesn't go positive then negative, positive then negative, positive then negative. It's kind of more sporadic. So there's a very irregular pattern of when it's positive and when it's negative. So it's not alternating series, so we can't use the alternating series test. All right, well, then what can we do? Well, let's take a look at the sum n equals 1 to infinity of the absolute value of sine of n over n squared. So I'm taking the absolute value of the top and bottom, but because n squared is always positive, I don't need to consider its absolute value. So what we're doing is we're looking at the sum of the absolute value of this thing. Now, if this converges, right? If this thing converges, if it converges, then that one converges. That's what that's what the theorem tells us. So hopefully this converges. So how are we going to do this? Well, now what we have is something where all of these terms are positive. So I can use anything from the previous section. So I'm going to do a comparison. I'm going to compare it. And I'm going to compare it to a series that I think that kind of looks like. I think it looks kind of like 1 over n squared. And this is a p series with p being 2, which converges. Now, when I compare it to this, I have the choice of using the inequalities, or I can use the limit comparison. I'm going to do the limit comparison. So I'm going to do the limit as n goes to infinity. I'm going to do this one here, absolute value of sine n over n squared over 1 over n squared. And what happens here? This isn't going to work. See, when I flip it, I get limit n goes to infinity of just sine n, right? And that as n goes to infinity, that goes, well, that doesn't exist. That limit doesn't exist because that's like this weird scatter plot of things. So that's not going to work. I'm going to have to compare it to something something else. Let me see. What's the comparison? What should we compare this to? It seems like that should have gone. Well, you know what? This is another great example of how sometimes this limit comparison doesn't work as well as the inequalities. Let's go, and instead of doing limit comparison, let's just do the traditional comparison where you have to do the inequality. So this right here is like the A sub n, and I'm comparing it to this B sub n. Since this one converges, the inequality that I want to show, okay, so I'm going back to the good old comparison test. I want to show that my A sub n's always stay smaller than or equal to my B sub n's, because these all add up to be a number, right? They converge. So I want to make sure these are smaller than those so that when I add them up, it stays smaller than that sum. So that means I want to show that the absolute value of sine of n over n squared is less than or equal to 1 over n squared, right? I can multiply both sides by n squared. I get absolute value of sine of n is less than or equal to 1. And that is always true because the sine function is bounded between -1 and 1. And so when you take the absolute value of it, it's got to be at the most 1, right? And it's got to be, what, bigger than 0, bigger than or equal to 0. So that is always true for all n, doesn't matter. So therefore, by the comparison test, not limit comparison because it didn't work, by the comparison test, this series, absolute value of sine of n over n squared, converges. But now what we can say, so by the theorem, the original series, before we took the absolute value, must converge. Because the theorem says if the absolute value of this thing converges, which we showed it did, then this must converge also. Interesting problem. When I first set this problem up, I was like, okay, I'm just going to do a limit comparison. Everything's going to be great. But the problem is this limit doesn't exist, so can't do it. All right, that's a really good one. I like that. Okay, we are at a really good point right now, 8.84.14. I'm going to take a quick break. All right, we have reached the point of the almighty ratio test. Now, the book does not call it the almighty ratio test, but this is one of the most important tests. We're going to use it a lot in the next section, a lot. So yeah, let's get to it. It's an awesome test. So the great thing about this test is that it can be used pretty much on anything. It doesn't matter if it's alternating, if all your terms are always positive, if even like the previous one with the sine thing, doesn't matter. You can always try this test. So it says given any series, okay, any series, doesn't matter what it is, then all you have to do is run this limit, okay? Take the limit as n goes to infinity of a sub n plus 1. What does that mean? Just plug n plus 1 into that formula. Then divide it by a sub n, which is the formula itself, and then take the absolute value. Take that limit and get some number. Hopefully it'll be a number. If that number is smaller than 1, you've got convergence. If that number is greater than 1, including infinity, okay, so anything greater than 1, even infinity, then it will diverge. The only time this test fails is if you take this limit and you get 1. If that happens, well, then the test failed, unfortunately. So there is possible that the ratio test could fail. Okay, let's see this in action. This is a great test. Like I said, we're going to be doing a lot of this. And there's some little nuances here when we start using the test that you need to start, to pay attention to. So here we go. We've got a series. Does it converge? Does it diverge? Let's do the almighty ratio test. Here it comes. So what I'm going to do is I'm going to set up a limit as n goes to infinity of the absolute value. And so what I'm going to do is I'm going to take this and I'm going to plug n plus 1 in everywhere I see an n. Okay, then I'm going to divide that by just the original formula there. Okay, take the absolute value of the whole thing. Now we have a fraction over a fraction. So if we have a fraction over a fraction, I can flip the bottom up and I will get the first part, or the top, the original top there. Now, yeah, I'll do it here for the n plus 1, and then times, now the other one flips up, comes up. So you get 4 to the n on top and negative 1 to the n times n to the 4th here. Now, a couple of things. First of all, does not matter what this is, does not matter what that is. Whether or not they turn out to be 1 or negative 1, when we take an absolute value, it's not going to matter, right? It'll make the negative a positive. So we don't care about those. Also, notice that this can be rewritten as 4 to the n times 4, right? That's just properties of exponents. And that means I can cancel that out. So let's see what we're left with. I have equals limit as n goes to infinity. Let's see, what's over here? Over here, we got n plus 1 to the 4th, and we have a 4 on the bottom. N plus 1 to the 4th, and then I have a 4 on the bottom of that. Times over here, we cancel that out, so we have a 1 up there, and then down here we have an n to the 4th. Okay, well, I can put those together. I get n plus 1 to the 4th over 4n to the 4th. All right, well, this right here is infinity over infinity, so I can use L'Hopital, but I think what I'm going to do is on the top there, the n plus 1 to the 4th, I'm going to expand that out. So I have to do n plus 1 times n plus 1 times n plus 1 times n plus 1, and then I have to multiply that all together. Now, what we do know is that the very first term, when we multiply all this out, the very first term is n to the 4th. And then we're going to have plus, and it's going to be a bunch of crap right here, right? Well, watch. Let me write this down. I'll do absolute value. I'll have n to the 4th plus a bunch of stuff down here over 4n to the 4th. And then when I take this limit, we know we're going to get infinity over infinity. So we're going to have to do L'Hopital over and over. All these terms will go away with L'Hopital. All you're going to be left with is the number in front here over this number here. So this is going to give you at the end 1/4. And that is less than 1, right? And according to the theorem, if we get a limit that's less than 1, we're going to have convergence. So therefore, the original series converges. There we go. All right, pretty cool, pretty cool. Let's do another one. Okay, does this one converge or diverge? Okay, same thing. I'm going to go ahead and set up the ratio test. Take the limit as n goes to infinity. Okay, I got to plug n plus 1s into all those. Careful here, n plus 1 to the n plus 1 over n plus 1 factorial. Okay, all of that divided by the original formula, negative 1 to the n to the n, all over n factorial. This is equal to limit n goes to infinity. All right, so I'm going to start not caring about the negative 1 to the n's. Those won't matter. I'm going to take this here, n plus 1 to the n plus 1 over n plus 1 factorial times, now take the bottom fraction, flip it up, so I got n factorial up here, and then over n to the n. And then that's equal to, okay, so let's see what happens here. We already have seen in this class several times that this becomes n plus 1 times n factorial, those cancel. And then the other one, the only thing I can say about these two, nothing cancels here. Let me do this. Let me do this. This right here becomes n plus 1 to the n times n plus 1 to the first power. So just using properties of exponents. And when I do that, this n plus 1 and that n plus 1 cancel, which is nice. So all I have up top is limit n goes to infinity, absolute value. So up here, the only thing left out of all of this is just an n plus 1 to the n over, and on the bottom, the only thing that's left on the bottom is n to the n. All right, both of those are raised to the nth power. So I can make that n plus 1 over n to the nth power. Whew. Okay, so this is a tricky problem because if we let n go to infinity, we get infinity over infinity here. L'Hopital on that would give us 1 over 1. So we know that this is headed to 1, but this is headed to infinity. So we have something that looks like this. And so in calculus 1, we have ways of dealing with this. Also, I don't need to worry about the absolute value because this for sure is never going to be negative. So I really am trying to figure out what this is. N plus 1 over n to the n. What is that limit equal to? Well, one thing I could do is because I have, on the inside, I have 2 terms over 1 term, I can split it into 2, n over n plus 1 over n to the n. And some of y'all might recognize that limit. It's a very special limit, very, very special. I'm going to act like you don't know what it is, and I'm going to go through the Cal 1 technique on how to solve this. And this is what we do anytime we see 1 to the infinity. We call this limit that we're looking for y. So we're trying to find out what y is. And then what we do is we take natural log on both sides of this equation. And when we do that, that allows us to bring this natural log through the limit right here in front of this. And that, the reason we do that is so we can bring this power down in front. Like I said, this is a Cal 1 topic, and you're talking about L'Hopital's rule. So n comes down here, natural log of 1 plus 1 over n. And now when you look at this, this goes to infinity. And when you plug infinity in here, you get 1 over infinity, that goes to 0. 1 plus 0 is 1, and natural log of 1 is 0. So this is now looks like infinity times 0, which again is a problem that you cover in Cal 1. And the standard technique to solve that is to drop one of them down. So what I mean by that is I'm going to leave the natural log of 1 plus 1 over n here. And I'm going to rewrite this n that was up next to it as a 1 over n in the denominator. So algebraically, these are exactly the same. N on top is the same as a 1 over n on the bottom. But by doing this, when I take the limit as n goes to infinity, I know the top here is going to natural log of 1, which is 0. But now the bottom, 1 over n, also goes to 0. So now we have 0 over 0. So now I can use L'Hopital's rule. Almost there. I got to take derivative of this. Derivative of natural log of something is 1 over it. Times the derivative of what's inside. Derivative of 1 is 0. Derivative of 1 over n is negative 1 over n squared. Remember, when you do that, that's n to the negative 1. When you take the derivative, power rule, negative 1 comes out. Subtract 1. That's the same as negative 1 over n squared. So that's the derivative of this. And then over the derivative of the bottom, which is the same as this, right? So negative 1 over n squared again. These cancel. So now let n go to infinity. You get 1 over infinity. That goes to 0. 1 plus 0 is 1. 1 over 1 is 1. So you get natural log of y equals 1. But remember, we wanted to know what y was, right? So now what we do is we apply the exponential function to both sides because that will kill off the natural log. And e to the natural log of y is y. So y equals e to the 1, which is e. Okay, so all of that, this right here, this limit goes to e. And e is about 2.718. That's bigger than 1. And according to the ratio test, if we get an answer that's bigger than 1, then this thing diverges. So our conclusion is that this diverges. That's messy. Most of the time, the ratio test won't be like this because this limit, you can figure out what it is pretty quickly. Here, we had to go figure that limit out and go back to Cal 1. So messy. All right, let's see this next one. This is a cool one too, because we've never seen a series like this before. So does this series converge or diverge? Whoa, this series looks weird. Let's see what's going on here. The first number is 2/5, 2/5. Then the next one is plus, now we do 2 times 6 over 5 times 8. Okay. And the next one is 2 times 6 times 10, and then 5 times 8 times 11. So it's kind of like the first one, but there's now a 10 and 11. This one's kind of like the one before, except there's a 6 and an 8. This one's like this one, but we've added a 14 over 14. So what's going on here? Notice that for each of these, like this is a jump by 4, right? We added 4, and then that's 4, and there's another 4 there, and then 4, 4, 4. We're jumping by 4 each time. And on the bottom, we're adding 3, right? 3 there, and then 3 more, and then 3, 3, 3. So let me see if this makes sense to you. What we have here is a sum, n equals 1 to infinity, where the numerator is going to be basically 2 times 6 times 10 times, and you're going to keep multiplying until you get out to, let's see, when we plug in 1, we need to get just 2 itself. So we want to stop this. These are all jumping by 4, so it's got to be a multiple of 4, 4n. If we plug n equals 1 in, we need to get just the 2. So how about we subtract 2? Okay, so let me try and again make sense out of what the heck this is. If n is 1, what do we get? Okay, I'm just worrying about the top right now. If n is 1, what do we do? Well, if n is 1, we're going to go 4 times 1. That's 4. Take away 2, that's 2. So I'm going to start at 2 and end when I get to 2. So just 2. Plus, let's look at the next one. Now n is 2. So plug 2 in here, you get 8. Take away 2, you get 6. So I'm going to go 2 times 6, but stop when I get to 6. So just 2 times 6. Plus, now when n is 3, I get 12. Take away 2, that's 10. So I want to do 2 times 6 times 10. Actually, stop when I get to 10. 2 times 6 times 10. Okay, now n is 4. So 4 times 4 is 16. Take away 2. 16 take away 2 is 14. So I'm going to go 2, 6, 10. And stop when I get to 14. 2, 6, 10. Stop when I get to 14. And then just for the sake of doing it, what would the next one be? Let's see. So this is 1, 2, 3, 4. If we plug in 5, we're at 20. Take away 2 is 18. So we want to do this pattern until we get to 18. 2 times 6 times 10 times 14 times 18. I hope that makes sense. That's kind of weird. We've never seen that before. Now on the bottom, it's the same idea. We want to do 5 times 8 times 11, and we want to keep doing that until we get to, okay, well, all of these jump by 3, so I have to put 3 in. But when I plug in 1, I want a 5. So I want to start at 5. So I'm going to add 2. Let's see if that works. Plug in 1, what do you get? 5, right? So you want to start at 5, end at 5. And when you plug in 2, you get 6 plus 2 is 8. So you want to go 5 times 8, stop at 8. When you plug in 3, you get 9 plus 2 is 11. So you want to go 5 times 8, stop at 11. Plug in 4, you get 12 plus 2 is 14. So 5 times 8 times 11 times 14. And then what are we at? 1, 2, 3, 4. Stop at 5. 15 plus 2 is 17. So we're going to go 5 times 8 times 11 times 14 times 17. And then we could continue on and on. All right, but the important thing is we've got a formula. Okay, this is a weird formula. I've never seen anything like this before. This whole thing in here is our a sub n. So let's try the ratio test. We want to take the limit as n goes to infinity of the absolute value of, first, we got to plug n plus 1 into this. So 2 times 6 times 10 times ... until I get out to 4 times, I'm replacing n with n plus 1, 4 times n plus 1 minus 2 over the same thing on the bottom, 5 times 8 times 11 times ... And then 3, replace the n with n plus 1. And then plus 2. All of that over this without any n plus 1s plugged in. So I'm going to copy it. Put it right here. Whoa, this looks like a mess. An absolute mess. So here's what I'm going to do. I'm going to rewrite it. All right, so this piece right here stays the same. Copy, paste. That's that. And then I'm going to take this bottom one and I'm going to flip it, put it on top. So that means this denominator goes up here. Oops. Try that again. That goes here. And then this 2 times 6 times 10 times ... 4n minus 2 goes here. And we want to know what happens here as n goes to infinity. Okay, so really, really an important step here. Let's make sure we understand that this, when you distribute the 4 through, this is 4n plus 4 minus 2 is going to be plus 2. This one, when you distribute the 3 through, you get 3n plus 3 plus 2 is plus 5. So that's this last one. So that's what these two are. Now, this, remember, the way this works is that these keep going up by 4 each time. So if I go backwards, the one before this would be 4 less than this. So if you take 4 away from that, you get 4n, take away 2. This one, they go up by 3. So if I were to go backwards on this one, I would take 3 away. So 3n plus 5, take away 3, you get plus 2. And what you'll see here is that you're going to start getting a bunch of canceling here. So like, look, this 5 would cancel with that 5, that 8 with that 8, that 11 with that 11, and everything here would cancel. And even this 3n plus 2 would cancel with that 3n plus 2. So everything in there is gone. The only thing left there was this piece. And then you also have that 2 and that 2 go, this 6 and that 6, that 10 and that 10, everything in the middle, ... And then that 4n minus 2 would even cancel with that 4n minus 2. And so the only thing you have left here is this. And so now here's where we are. We're at limit and goes to infinity, absolute value. I mean, look, everything is gone except the yellow parts, 4n plus 2 over 3n plus 5. And one application of L'Hopital on that, because we have infinity over infinity, you just get 4/3. And that's bigger than 1, which means we have divergence. Ooh, that's weird. Okay, there's a couple problems in the homework like that. It's good. These are good problems. I really like these because you have to understand how to create a formula from this. So you've got to see patterns, and then you got to know how to expand it out properly to make things cancel. All right, we're almost done. We have this last test. Okay, the ratio test is the big one. The root test here is the last test in this section. It's not used very often, but we need to know about it. It basically says that if you have any series, again, doesn't matter what the series is, if you take the limit as n goes to infinity, kind of like the ratio test, but you don't do a ratio. What you do is you take the nth root of the you do the nth root of the absolute value of the sequence, and then same things like the ratio. If you get an answer that's less than 1, it converges. Greater than 1, it diverges, including infinity. And if it is equal to 1, you get no, inconclusive. So I'm going to do both of these. This is going to go quick because this root test works really fast usually. So let's start with this first one. So I look at this and I say, the big thing that is going to make me want to do root tests is the fact that I've got a power of n out here. So when I do the root test, what I'm going to do is I'm going to take the limit as n goes to infinity of the nth root of the absolute value of my sequence formula. Okay, now the absolute value of this, the absolute value doesn't matter because we know this is positive. This is all positive and this is positive power. So we don't really need to consider the absolute value. So we really just want the nth root of 3n plus 1 over 4n plus 3 to the n. And the whole thing that's great about the nth root test is that if you have a power of n, you're going to take the nth root. So the nth root and the n go away. So you just get 3n plus 1 over 4n plus 3. And if you do L'Hopital one time, you'll get 3/4, which is less than 1, which means you have convergence. So this one converges. Now, if we do the next one, again, see the n squared there? What you need to understand is that this is really 1 plus 1 over n to the n to the n, because you would multiply these two together, and n times n is n squared. So that's what that really is, all right? So I'm going to use the root test here. So if I do the root test, I'm going to take the limit as n goes to infinity of the nth root of, now again, the absolute value I'm not going to pay attention to because n is always 1 or greater, these are always going to be positive numbers. So I'm not worried about an absolute value, it's the same thing. So I'm going to do the 1 plus 1 over n to the n, but all of that to the n. And then this root kills off that outside n, which leaves me with a limit as n goes to infinity of 1 plus 1 over n to the n. I still have one of those n's there. And I need to figure out what this is. If it's less than 1, we have convergence. If it's greater than 1, we have divergence. And you should recognize that from what I did a moment ago. This, remember that? We were trying to figure out what this was, and we said it was E. We know this is E, which is greater than 1. So we have divergence. Okay, that's it for 3-4. You got to work through the homework problems here because there is a ton of material in this section. Hope it goes well. I hope this helped.